Albert Einstein was a renowned physicist who formulated the theory of relativity, which consists of two main theories: special relativity and general relativity. Special relativity. 1. Principle of relativity. The first postulate of special relativity states that the laws of physics are the same for all observers in uniform motion. In other words, there is no preferred or absolute frame of reference. Observers moving at constant velocity relative to each other will see the same laws of physics. 2. Constancy of the speed of light. The second postulate introduces the idea that the speed of light in a vacuum, denoted by c, is constant for all observers, regardless of their motion. This means that the speed of light is independent of the motion of the source or observer. 3. Time dilation. One consequence of special relativity is time dilation. Time appears to pass more slowly for an observer in motion relative to a stationary observer. This effect becomes significant at speeds approaching the speed of light. 4. Length contraction. Length contraction is another consequence, stating that an object in motion appears shorter in the direction of motion when measured by an observer at rest. 5. Mass-energy equivalence, E equals mc squared, asserts that energy, E, is equivalent to mass, m, times the speed of light squared, c squared. This equation implies that mass can be converted into energy and vice versa. General relativity. 1. Equivalence principle. The equivalence principle is a cornerstone of general relativity. It posits that locally, the effects of gravity and acceleration are indistinguishable. In other words, an observer in a gravitational field experiences the same effects as an observer in an accelerated reference frame. 2. Curvature of spacetime. Einstein proposed that gravity is not a force between masses, as described by Newtonian physics, but rather the result of the curvature of spacetime caused by the presence of mass and energy. Massive objects, like planets and stars, create curves or dips in the fabric of spacetime. 3. Gravitational time dilation. General relativity predicts that time passes more slowly in stronger gravitational fields. Clocks at lower gravitational potentials run slower than clocks at higher potentials. 4. Gravitational redshift. Light waves traveling out of a gravitational field experience a gravitational redshift. This means that light emitted in a strong gravitational field appears shifted toward the red end of the electromagnetic spectrum. 5. Frame dragging. General relativity predicts that a rotating mass will drag spacetime around it. This phenomenon is known as frame dragging, and it suggests that the rotation of a massive object can affect the motion of nearby objects. Summary. Einstein's theories of relativity revolutionized our understanding of space, time, and gravity. They have been extensively tested and confirmed through experiments and observations, making them fundamental pillars of modern physics. The theories have far-reaching implications, influencing our understanding of the cosmos, the behavior of massive objects, and even technologies such as GPS systems, which must account for relativistic effects to provide accurate measurements. In essence, Einstein's theories of relativity have profoundly shaped the way we perceive and understand the physical universe.